Welcome to the optical communication course. So today we will learn that a avalanche photodiode. So we have learned earlier that is about a pin diode. So in a pin diode, for a given incident photon, it will generate a electron hole pair. As for a single incident photon, it will generate a single electron hole pair. So means we can say that for a electron hole for a given photon, it will generate only one electron hole pair. And because of this, the efficiency of a pin diode is very low. So efficiency is nothing but we say a quantum efficiency of the given diode, it will be very low because that efficiency is nothing but number of electron hole pair generated based on the incident photon. Now to improve the efficiency of the diode, so that another diode is developed, and that is the avalanche photodiode. So in which what happen, for a given incident photon, it will not generate only a single electron hole pair, it will generate a multiple electron hole pair. So that's why this avalanche photodiode is called the multiplier, or we can say that the avalanche multiplication takes place inside this avalanche photodiode. So that's why avalanche photodiode APD, it will generate a large output current as compared to the pin diode because it will generate a multiple electron hole pair. So that's why there will be a large current produces by this. And because of this large current produced by this avalanche photodiode, so after the detector, we require a amplification circuit. Generally, what happen here? We have the fiber, then we have the detector, and after that detector, we require a amplifying circuit. So whichever the circuit we are using as amplifier, whatever the detected current, that will be amplified. But in the case of a pin diode, that current is a small because of a small number of electron hole pair generated inside the pin diode. But in the case of avalanche photodiode, multiple electron hole pair generated. That's why the large current is generated. So if you consider that at a receiver, so we doesn't require sometimes amplifier. Even if we require the amplifier, but that amplification required will be less as compared to the pin diode. Now, how this avalanche photodiode produces a multiple electron hole pair, because that avalanche photodiode operate on a large reverse bias voltage, large reverse bias voltage, and due to the large reverse bias voltage, it has a high field region. It has a high field region. That high field region, within that a device, and because of this high field region, this will accelerate the photon generated electrons, and they acquire the kinetic energy from them, and then they collide on the bonded electron in the valence band and create a secondary electron hole pair. Because of the high field region, it will generate a secondary electron hole pair. And this process of generation of the electron hole pair is called as a impact ionization. It's called as a impact ionization. If this field is created because of a large reverse bias, if it is a large, then that secondary electron hole pair that will create again a new electron hole pair. Means from the single electron hole pair, it will generate a secondary electron hole pair. From the secondary electron hole pair, it will generate a new electron hole pair, and this effect is called as a avalanche effect. This effect is called as a avalanche effect, and that's why we can say that that electron hole pair it is a multiple in this avalanche photodiode, or we can say that carriers get multiplied, and because of that multiplication of a carrier, there will be a large current produced. So you'll get that output current or a photo current will be large because of this multiple electron hole pair generation. Now, if you see the schematic of this avalanche photodiode, so it has a N plus region, then a P, then we have the I that is intrinsically here, and a P plus. Plus means what? A highly doped. Okay, N plus highly doped, P plus highly doped, and this P is a lightly doped. Okay, and this one is about a intrinsic layer, or some books they have mentioned that a pi layer for this given diode. And a photon is incident on this N plus layer, and this one is a metal contact, metal contacts here, and that will connect it to the whatever the reverse bias voltage, and then we will get the output. And if you consider their electric field variation, likewise we have the electric field, and this one we have the direction here. I'll just draw this line here. Okay. Now, if you see that what happened because of that large risk bias voltage we are applying, so in that this particular junction N and P here, so it will generate a high gain, or you can say that this is about a high field domain because we have the high electric field. This one is about a high gain region or a high electric field region, and that is region is called as a avalanche region Here the multiplication of electron and hole pair generated. So we require some maximum field for the impact ionization. This is about a maximum field. Maximum field required for impact ionization. Now above this, okay, above this, so then multiplication of electron and hole pair is generated there, and then because of that, we'll get the large output current. Now if you see that here is a n plus layer, this layer is a very thin layer. N plus layer is a very thin layer because photon is to be emitted from this particular layer, and that is propagating through this layer. Okay, that is nothing. So that's why this one is about a thin window. And then we have this p-type material here. Then we have the another p-type material that is a highly doped here. But if you consider that this one is about, because incident light is to be emitting from this so thin layer n plus. Similarly, this one is again a thin layer, and this one layer will be a thick layer. And this one we can say a thick layer again, and this one is about a intrinsic layer. And this one layer is about a highly doped, because a P plus means highly doped layer. So this one is about a thick, and is about a highly doped layer. We can say that because in the dimension wise, we will say just like a highly doped here, and because the incident photon is to be emitting from this n plus p to this particular intrinsic layer. So this one is about a depletion layer under the no bias condition. So and this diode will work when we apply the reverse bias voltage. When we increase the reverse bias voltage, then the field will be increases, and that field here we can say that field will be increases because we are increasing the reverse bias. So when that photon falls in this particular layer, that is about, we have the this junction is about n plus p junction, and here the photon will emit in this particular layer, so it will generate the electron on hole pair. Okay, so means number of, that is about a electron and hole pairs are generated in this particular layer. And if you see the field, here it is at this particular junction, it will be high here, and the field, if you see that the field is constant here. So throughout this particular layer, that field is uniform, and that will separate that electron and hole pair in this particular region. And then that electrons and holes, that pairs are generated, and that pairs, because of this high field, they drift toward the n plus and a p plus region. Okay, we say that this one, here we have a electron and hole pair, they are drift toward this n plus and a p layer there. When these electrons are reached to this particular p layer, because it is to, electron is to be moved toward the n plus, hole, we say It is for this layer. Okay. So, so we can say that we have the electron and hole pair moving toward this particular junction. When the electrons will reach to this particular p layer, in that case they experiences this high field region. Okay, they experience a high electric field, and they acquire a sufficient kinetic energy, and that energy is greater than the band gap of energy. So that's why that they get the energy to impact the ionize some of the silicon covalent bonds, and then they will release the another electron hole pair here. Now these electrons again further cause the impact ionization in this particular region because of this high field, and then it will release the more electron hole pair in this particular region. And that is about a number of electrons and hole pair generated more, and this chain or this process is called the multiplication process of the electron and hole pair in this particular region there, and that is called as a avalanche impact ionization process, because it will generate a multiple electron hole pairs in this particular region. So that is called as a avalanche impact ionization process. So means we say that a one electron hole pair generated, and that then electron will enter in this particular region, in this particular p region. So it will generate a more number of a electron and hole pair in this layer. Because of that number of electrons and hole pairs are more generated in this region, so it will create a current, and that current is depending upon that multiple EHPs, multiple electron and hole pairs. So that's why the current will be in a multiple nature of this electron and hole pair. So we say that because of that multiple current generation takes place in this region, and that process is called as that process is called as the internal gain mechanism of this particular avalanche photodiode. Because a photo generation takes place, we say that in this intrinsic region, and the avalanche multiplication takes place in the p region. Here the photo generation means electron hole pair generation takes place in this I region, and avalanche generation takes place in this particular region, and that avalanche process or avalanche multiplication process, that will generate the avalanche photocurrent. So the avalanche multiplication factor for this avalanche photodiode is depending upon that how much will be the multiplied output current generated based on the initial multiplied photocurrent, unmultiplied photocurrent. So we can calculate that a avalanche multiplication factor, that is M, is equal to a multiplied output photocurrent divided by initial or a primary unmultiplied photocurrent. Means what? This one is what? So before generation of the more EHPs, that current, and this one is about after generation of the more electron hole pair EHP, so that we will get that multiplied output current. Okay, multiplied output photocurrent we are getting, and that is equal to M is equal to 1 by 1 minus what will be the input voltage and a breakdown voltage. So VBR is a breakdown voltage and V in is the reverse bias voltage, and N is nothing but the characteristic index of the given particular material. And then this particular process of multiplication, so that process called as a speed of reach through APD, or we can say that a rapid generation of this particular APD there. So in all other books they have used that reach APD because it will generate a more number of a electron and hole pairs. So that's why they are APD there. That reach APD means what? Or how that generation or speed of that reach APD, it will depends upon the how much is the time taken for the photo generation, or we can say that photo generated electrons there. Time taken for a photo generated electrons to cross the absorption region. To cross the absorption region. That is called the intrinsic region to the multiplication region. Now here the photon generation takes place, then electron will cross to this particular region. Here the multiplication takes place. So that is called the multiplication region. That is about the speed of this reach APD is depending upon that electron will cross from this layer to this layer. So how much is the time taken for the electron to cross this region there? Because this one is nothing but what? A absorption region. This one is a called as a absorption region. And here another is about what? A time it takes for the avalanche process to build up in the P region to generate the EHPs. Time to generate the EHP in in P region. In a P region. So reach APD depending upon that how your electron hole pair generated in this particular region there. So that's why that response time of this particular APD we can calculate similar to this phone pin photodiode, that is response time or responsivity of this APD is equal to NQ by HV RM. Sorry, that is M here. I'll write again here NQ by About m here. And that R is nothing but the unit again responsivity. So that is about if you see that again this responsivity, it is again depending upon that what will be the wavelength there, what will be the wavelength of the particular source, and that ionization takes place in the given electric field, because here we say that a ionization takes place. So if you consider that a different material and a ionization process with respect to the electric field, so in that case, for the silicon, number of holes electron pair generated is likewise. Okay, that is about the ionization process. It will be that graph will be a likewise there with respect to the electric field there. And if you see that how much is the voltage applied, according to that a current is generated. So this one is about a current gain here. We have the voltage, because for a given particular photodiode we apply a bias voltage. So according to the given particular bias voltage, so this one is about a generation of 100, 200, 300. This is about nothing but a bias, and this one is about a current gain. 2, 4, 10, 20, 50, 100, likewise. So gain is increased here when we apply the bias. So there are some drawbacks of this avalanche photodiode. So if you see that in the avalanche photodiode, so we require a thin layer, thick layer, likewise. So that's why designing this particular structure, so fabrication cost will be a more. And again, another one is what? Here it will generate a excess electron hole pair, or because of this we can say that a avalanche multiplication, it will generate a more electron hole pair, and that process is nothing but a statistical process, and that will fluctuate a carrier generation, and then it will generate the excess noise in this avalanche photodiode. Again, it will require a high field, as per the high field value. How this high field domain is generated, electric field is generated, because of that high voltage we have to apply. So means this avalanche photodiode requires a high bias voltage, so that it will produce a high gain current. So this is about a gain current, because of the we require the high bias voltage. And then gain is again depending upon the temperature. So that's why for a given particular circuit we require a temperature compensation circuit for the stable operation of a avalanche photodiode. So for the given particular material, if you consider that a pin diode and a avalanche photodiode, with respect to the parameter that is about the wavelength, and if it is a silicon and a germanium, and again it is for the silicon and germanium, so operating wavelength is about what? Lambda here, 0.4 to 1.1, 0.8 to 1.8. That all the values in a micrometer. And if you consider that avalanche photodiode, again its operating wavelength is about same 1.1, 4.4 to 1.1 to zero point 0.8 to 1.8. But if you consider that responsivity, so in that case for the pin diode and for this avalanche photodiode, it is about zero point 0.4 to zero point 0.6. here 0.5 to 0.7. And if you consider this avalanche photodiode, it is about to 80 to 130, and here 3 to 30. That is about the responsivity. And that gain, avalanche photodiode gain, because the gain is not there for the pin diode, but gain is for the avalanche photodiode, it is about the 100 to 500, and it will be for 50 to 200 here. That M, okay, M factor. And if you compare with the bandwidth of your operation, so it will work for the bandwidth is in terms of a gigahertz there, zero point 0.3 to zero point 0.6, and here 0.5 to 3, and here zero point 0.2 to 1, zero point 0.4 to zero point 0.7. That is about the bandwidth of operation. So now same material. So if you construct a pin diode, then factors are different, and if you construct that APD, then these factors are different. Why? Because that applied bias voltage is different for this pin diode and APD. So if you consider that a bias voltage applied, reverse bias voltage for this pin diode, it is about the 50 to 100, and here for the germanium it is for the 6 to 10, and for the avalanche photodiode it will be for the 200 to 250, and it will be for the 20 to 40 there. So if you compare the bias voltage, so it is a large. For the germanium, again it is a large. So that's why that parameter, all parameters are depending upon that applied bias voltage and a responsivity. That is about your avalanche photodiode and a pin diode here. Now then, there are the types of a modulation circuit we require, because if you consider that a source, that may be a LED or a laser. So in that case, what we require a separate modulation circuit to convert that electrical signal to the a modulated light. So if you consider that a source, that may be LED or a laser there, so we provide the electrical input to this, or electrical modulating signal, and then here it will generate that light. That is about the modulated light output, electrical modulating signal. Means we have this 1 0 1 0, means what? That light will be off on off likewise. It will generate that on off likewise. If it is a 1, it will be on. If it is a 0, it will be off. And that modulation is called as a direct modulation. That modulation is called as direct modulation. Means based on this particular input drive current, whichever the pulse we have, according to that, it will generate that a light. And another is about what we can say a external modulation. In the external modulation, we have the source, and the source will generate a light output. Source will generate a light output. And then light output is converted using the modulator here. This light is given to the modulator, and to the modulator we have to give the electrical modulating signal, electrical modulating signal, so that it will generate a modulated light output, so that it will generate a modulated light output. Means in external modulation, we require the external modulator. So whichever the light is generated using the external modulator, so we can generate a modulated light output. So again it will use 10110 likewise. One is say on and 0 is again say off. It is similar to this one, direct modulation. But in this case, direct modulation, electrical signal directly converted to a light, and here light is the input. Here we require external modulating circuit or a modulated device. So it will generate that electrical signal into a light there. So that is called as a external modulator. So that is about a modulation of a light emitting diode. Now we will see that few MCQs, and then we stop here. Now operating wavelength of gallium AS light emitting diode LED and lasers are A 820 and 850 nanometer, B 665 nanometer, C 1300 nanometer, and D 1550 nanometer. So answer for this you can type in a chart there. The next is about light emission from an LED is modulated by A applied voltage, then B drive current, then C illumination, and D all of the above. Now if you see that first, operating wavelength for gallium arsenide ALAS light emitting diode and laser, it will be operated at the 820 to 850 nanometer of a wavelength there. Now if you consider the second, light emission from an LED is modulated by, just slightly we say that whichever the current pulses are there, that will be given to the light emitting diode, and then it will generate the photon of the energy. So that's why it is depending upon that a drive current. Third, a material for making an efficient LED should be A metal, B insulator, C a direct band gap type semiconductor, and D and indirect band gap type semiconductor. Now, if you see that a material for making an efficient LED, so we require a direct band gap type of a material because that conduction band and a valence band, we have that electrons and holes. They will be that momentum at that particular momentum, they will be directly interacted. So maxima of this valence band and minimum of this particular conduction band, that will be at same particular position. So that's why it is called as a answer for this. That is about a direct band gap of a material here. The difference between laser and LED is a semiconductor material, then B, structure of device, that confine light, and electrical current to produce laser action. C, high drive current used for laser, and D, both B and C. If you type the answer, that is the both B and C, means that D is correct here. That is about it, both D and C. Next, a spectral width of LED is typically, that is 1 to 20 nanometer, then B 30 to 50 nanometer, then C 100 to 200 nanometer, then D greater than 200 nanometer. Type your answer for this. Spectral width. Yes, correct. That answer, that B is correct. Someone has written that answer, that B. It is correct, 30 to 50 nanometer. Then next one, the spectral width of laser typically, that A1 to 3 nanometer, B zero point 0.1 to 0.5 nanometer, then C 3 to 10 nanometer, and D 10 to 30 nanometer. What is the answer for this? Spectral width of a laser. Yes, correct. It is about a 1 to 3 nanometer. Next, we will see that fiber optic photodiode detectors are normally A. Forward biased, B. Reverse biased, then C. Unbiased, or we can see that is about it. Thermoelectrically cooled. What is the answer for this? Fiber optic photodiode detectors are forward bias, reverse bias,